So continuity, day number 2, we'll talk a little bit about intermediate value theorem and the special limit as x goes to 0 of sine x over x. Okay, so does anybody remember off the top of their head this limit? This is a special limit. It's either 1 or 0, right? Who wants to take a guess at 0? You're going 0? You're going 0, okay. Actually, let me write the other one up here. Okay, one of those is 1, one of those is 0. First one's 0? First one is 1. Second one is 0. Sine of x is 0, but 0 over 0 could be indeterminate, so then we use L'Hopital's rule. And the derivative, what's the derivative of sine x? Cosine x. And what's the derivative of x? 1, and if I plug in a 0, I get cosine of 0, which is 1 over 1. Okay. Let's do this. Let's go old problems, skip those, skip them, skip them, skip them, skip them. Okay. I am not going to formally, guys, I'm not going to formally prove this today. We could find and prove sine of theta over theta equals 1 using this, what's called the squeeze theorem. Basically, the squeeze theorem is I find something that's always bigger and something that's always smaller, and then I show that both of those go to 1, and therefore whatever's in between them has to also go to 1. That's the basis of the squeeze theorem. We can I can record that and just post it. You can watch it if you want. I'm not doing the proof right now. I don't really care about that right now. Let's get into some of this good stuff. So if I know that the sine of theta over theta equals 1, then this limit I could rewrite as theta goes to 0. I could write sine squared theta as sine theta times sine theta over theta. Now, what I know is that this, as theta goes to 0, goes to what? 1. And that, as theta goes to 0, what is the sine of 0? 0. So 0 times 1 equals 0. So the limit of that function, sine squared theta over theta, goes to 0. Let's see how we can maybe adapt and change this one so that it would work for us. What could I do here? Here's a trick. As theta goes to 0, let's say that I have, let's call this, no, let's not call it theta. Let's call it psi. All right, let's set psi equal to 3 theta. So what would theta equal? If psi equals 3 theta, what would theta equal? 1/3 psi, right? Or psi over 3. What's the same thing as dividing by a fraction? Multiply by its reciprocal. So couldn't I say this is true? Couldn't I do that? I divided by 1/3 here, right? This is 1/3 psi. Instead of 1/3 psi, I could, dividing by that, I could multiply by 3 over 1. So what is this? Okay, let's go back then. Let me pause it. Okay, instead of dividing by that 1/3, I'm just going to multiply by 3. Because I got to change that. I got to change that variable. Instead of dividing by that, I multiply by this, and the sine of theta over theta, or psi over psi, is equal to 1. Let's record this. Theta over, I'm going to turn this into sine over cosine. Dividing by that is the same as multiplying by what? Yeah, cosine over sine. So this would be the same as theta times cosine theta over sine theta. Well, what would, now let me rewrite it again. I'm just going to adapt this. I'm not changing anything. I'm just moving some stuff around. What would that equal? 1. That's just 1. And cosine theta, this is 1. Limit of theta goes to 0 of just cosine of theta. If I plug a 0 in there, what do I get? I get 1. Because the cosine of 0 equals 1. I'm going to talk through it. F of x is continuous at x equals c if these 3 things happen. First of all, f of c has to exist. F of c exists. So there can't be a gap in the graph. Okay, well that makes sense. Continuity has to have continuous values for outputs. The second thing that has to exist is that the limit as x approaches c of f of x has to exist. So you can't have some kind of jump. Right? It can't jump. And the last thing is that the limit as x approaches c of f of x has to equal f of c. This is a whole lot of math jargon for this. Here's c. Here's f of c. I'm saying this. As we come from the left and as we come from the right, that limit must exist. That's step 2. So step 1 right now is a failure, so this is not continuous until the limit equals the value at f of c. Now it's continuous. That's basically math language for don't ever pick up your pen. Make sure it goes straight through that point. There's no gap. No jump. This would be a failure. That would be a failure at x equals c, right? Because f of c does not equal the limit of f of x, which doesn't exist anyways. So, okay, that's continuity. The intermediate value theorem, all it says is this. Oscar, if continuous growth happens, that along the way, there's a value everywhere. There's an output for every input. So let's look at, real quick, the intermediate value theorem. If a function is continuous, then every output between the beginning of that function and the end of the function exists. Math language for that right there. Math language what? Yeah, don't be an idiot. Intermediate value theorem. If I tell you that a function is continuous, then it's continuous. If I tell you this function, right, f of x is continuous, and I'm telling you right now on the AB exam, there's at least one question on this every time. Every time. It says, okay, f of 2 is 7, f of 7 is 5. Prove that there is some c value such that where c is between 2 and 7, right? If this is continuous, there better be values in between that equals, I don't know, let's say 6. Wouldn't it make sense if I have a function that's continuous, I'm told it's continuous, and they might sneak it in on you and say it's differentiable. Well, if it's differentiable, it has to be continuous. So let's say f of 2 is 7. And f of 7 is 5. If it's continuous at some point, there has to be a c where f of x is 6. It just has to happen if it's continuous. It has to. Could it happen more than once? Sure. But if it's continuous, then there has to be a value in between which satisfies that. Could I have changed this to 6.8? Yep. 5.1. Sure. Doesn't matter. Any arbitrary value between 5 and 7. Doesn't matter. That's the intermediate value theorem. Basically, it says don't be an idiot. Understand continuity. That's it. I think that's enough for